So we've been over a number of methods for anti-differentiating, and I just want to cover in this section a couple of more that aren't used as extensively as some others, but they're very convenient and very useful at the right times. And it also, they're substitutions involving hyperbolic trigonometric functions. So we're going to concentrate on hyperbolic sine and hyperbolic cosine. You may have keys for those functions on your calculators, or they may be menu choices, but you may not even know the definitions of hyperbolic sine and cosine, so I am going to define them. Once you have hyperbolic sine and cosine, we won't, but we could define the other hyperbolic trigonometric functions like normal tangent is sine over cosine. So hyperbolic tangent, you could define it to be hyperbolic sine divided by hyperbolic cosine, but we're just going to look at hyperbolic sine and cosine. So, all right, what are these things? So hyperbolic, and I will explain why they're called hyperbolic. Hyperbolic sine and cosine, these are abbreviated. I use my handwriting, my cursive here, because otherwise this kind of looks like S times N, I times N times H. It's abbreviated, well, sine, how we abbreviate sine, but with an H after it for hyperbolic. It's pronounced, when people say this out loud, they say it as though there's also a C here. Everyone says cinch, because sinha just sounds stupid. This is usually abbreviated cinch, and hyperbolic cosine is usually abbreviated COSH, and that's pronounced phonetically, cosh. So, cosh, and their definitions are, and these don't look very trigonometric, I'll comment, or much like the normal trig functions, but I'll comment on that. This, by definition, hyperbolic sine of x is e to the x minus e to the minus x over 2. And hyperbolic cosine, cosh of x, you change that to a plus. E to the x plus e to the minus x over 2. It's hard to see that these in any way, shape, or form resemble ordinary sine and ordinary cosine. Later in the book, when we've done infinite series, and in particular have Euler's formula will relate complex numbers, will take complex numbers and relate raising e to powers to ordinary sine and cosine. And once you have those, you can see that hyperbolic sine and hyperbolic cosine are closely related to ordinary sine and cosine if you're willing to use the square root of -1 in places. But we're not going to do that now. But what are a bunch of the properties of hyperbolic sine and cosine? You can read many of them off immediately. So for instance, hyperbolic sine, this is an odd function, because if you replace x, so this is odd, it's an odd function, because if you take hyperbolic sine of -x, you get e to the, so you replace that x by -x, you get -x minus e to the negative x, so that's e to the positive x over 2. But this is exactly the negation of that, so yes, this is negative hyperbolic sine of x. So yes, hyperbolic sine is an odd function. Hyperbolic cosine is an even function, because, in fact, I won't even write out kind of a formula for this, because well, I guess I will. Because hyperbolic cosine of -x, you simply replace that by a -x, this by -x here, so that's -x, you get e to the x plus e to the minus x. Back again, they're just written in a different order. So this is even. Okay, great. What else can we see immediately? Well, e to the x is always positive. E to the negative x is always positive. E to anything, or any positive base raised to a power is always positive. So this number is in fact hyperbolic cosine is always, I'm going to write, for right now, I'm going to write that it's always greater than 0. But in fact, we're going to see in a minute that it has a minimum value of 1. Hyperbolic sine is certainly not always greater than 0. If you take x to be negative, like if you take, you can do this in your head. If you take x to be negative and large, and if x is negative and large, this part is, well, e to a negative large number is 1 over e to a large positive number. So if x is negative and negative of a large number, this is very close to 0. This is something negative, the negative of something large, so this would be a large positive number, and you'd have negative that. So hyperbolic sine of x can be negative. In fact, we'll see that it goes to negative infinity as x goes to negative infinity, and infinity as x goes to infinity. Let me go ahead and sketch the graphs, and then we'll verify the properties that I just stated. So we'd like to see quickly that the graph of y equals hyperbolic sine looks roughly, well, the way I draw it, it practically looks like the graph of y equals x cubed, but it's very different. So this is the graph of hyperbolic sine. What you're supposed to get out of this is that it's odd. The function's odd, so that the graph is symmetric about the origin. As x goes to infinity, hyperbolic sine goes to infinity. As x goes to negative infinity, hyperbolic sine goes to negative infinity. It actually does those things very quickly. The function is always increasing, and it's concave up when x is positive and concave down when x is negative. Hyperbolic cosine has a minimum value of 1. Its hyperbolic cosine is even, so its graph is symmetric about the y-axis. As x goes to infinity, y goes to infinity. As x goes to negative infinity, y still goes to infinity. This function is increasing when x is positive, decreasing when x is negative, and the graph is always concave up. How do you see these things? Well, we use calculus. We take derivatives. So we need the derivatives of sine and hyperbolic sine and cosine. But those are easy. It's easy to take the derivatives of these things because we know how to take the derivatives of sine and of e raised to powers, and we know the chain rule. So if you want the derivative of hyperbolic sine, so I'll put the derivative symbol there, it's just this. The 2 is a constant, so we can just pull that out. The derivative of e to the x is e to the x. The derivative of e to the negative x, you get, so I'll put this minus sign back, you get the e to the negative x, but by the chain rule, you have to multiply times the derivative of negative x, so you pick up another multiply by negative 1, but I'll put that here. Oh, this is hyperbolic cosine. Yes, the derivative of hyperbolic sine is hyperbolic cosine. The derivative of sinh is cosh. You might think in analogy with ordinary trig functions that the derivative of hyperbolic cosine would be negative hyperbolic sine. That is not right. The derivative of e to the x is e to the x. The derivative of e to the negative x, as we just said, is negative e to the negative x. So, yeah, the derivative of cosh is sinh. So unlike ordinary trig functions, which when you're talking about hyperbolic trig functions, you frequently refer to the ordinary trig functions as circular trigonometric functions. unlike ordinary circular trig functions, the derivative of hyperbolic cosine is not negative hyperbolic sine, it's hyperbolic sine. It's easy to derive if you should forget it, as long as you remember the definitions of sine and cosine. But we said that it was easy to see that hyperbolic cosine is greater than 0. So the derivative of hyperbolic sine is always positive. That means that the function is always increasing. That's what I drew in the graph. It's also true that the second derivative, right? If the derivative of hyperbolic sine is hyperbolic cosine and the derivative of hyperbolic cosine is hyperbolic sine, then it's true that the second derivative of hyperbolic sine is hyperbolic sine again. So if you take two derivatives, you get back where you started. But it's easy to see that hyperbolic sine, in fact, I should have done this, it's easy to do the algebra, that hyperbolic sine, which is this, so I'm not drawing it under the hyperbolic cosine here. I'll put it over here. That hyperbolic sine this is greater than 0 exactly when x is greater than 0. 0 when it equals 0, when x equals 0, and is negative when x is less than 0. Right? This is actually easy to show because of what we know about e to the x. So you want to know where, let me just do one of these. For example, well, certainly when x is 0, you get e to the 0, that's 1, minus e to the 0. So yeah, you get 0 when x is 0, but how do you see this one? That when x is greater than 0, e to the x minus e to the minus x over 2 is greater than 0. Well, obviously the denominator doesn't matter. How do you see that e to the x minus e to the negative x is greater than 0 when x is greater than 0? I'll do a bunch of if and only ifs. So when is this true? Well, that would be if and only if I can multiply this equation by anything positive and it won't change the inequality. But e to the x is always positive. So multiply this this inequality by e to the x. You get e to the x times e to the x is e to the 2x minus e to the x times e to the minus x is 1 is greater than 0. Oh, well that's if and only if e to the 2x is greater than 1. But we know when e to something is greater than 1. When is e to an exponent greater than 1? When the exponent is greater than 0. And so this is if and only if, cram it in down here, if and only if 2x is greater than 0, but that's the same as x being greater than 0. So what does this give us? This gives us, oh yeah, we already saw that hyperbolic sine is always increasing. Its second derivative is hyperbolic sine, and that's positive when x is positive. So the second derivative is positive when x is positive. So you see that the graph is concave up. I didn't do it, but it was an if and only if. So this will be negative when x is negative. So the graph is concave down when x is negative. So yeah, the only thing left to verify is that when x goes to infinity, hyperbolic sine goes to infinity, and as x goes to negative infinity, hyperbolic sine goes to negative infinity. Well, we can get one of those by symmetry. So as x goes to infinity, why does hyperbolic sine go to infinity? Well, that's easy too. As x goes to infinity, I'm rushing through this because we really want to get to how this relates to integration. So these derivations, most of these are exercises in the book. You're supposed to do these, so I'm giving them away. But why is why does this go to infinity as x goes to infinity? As x goes to infinity, certainly we know e to the x goes to infinity. As x goes to infinity, e to the negative x, well, that's 1 over e to the x. As x goes to infinity, this part goes to 0, so we end up with infinity minus 0 over 2. That's infinity over 2, that's infinity. Yes, as x goes to infinity, this goes to infinity. The graph looks like this. Y is hyperbolic cosine, y prime is hyperbolic sine. But we just said that that's positive when x is positive and negative when x is negative and 0 when x is 0. That means exactly that, so the derivative is positive when x is positive. So the graph, we see that the function is increasing. The original function is increasing where the derivative is positive. The original function is decreasing where its derivative is negative. So that's where x is negative. And it reaches a global minimum at x equals 0. And why is that at 1? Because when x is 0, we have the hyperbolic cosine of 0, which is e to the 0 plus e to the 0 over 2. And that's 1. So, and the second derivative of hyperbolic cosine is hyperbolic cosine again, which we now know is greater than or equal to 1, but in particular it's positive, so that the graph is always concave up. Once again, how do you know that as x goes to infinity, hyperbolic cosine goes to infinity? Because as x goes to infinity, this goes to infinity, this goes to 0, infinity plus 0 over 2 goes to infinity, and then by symmetry, you can get that as x goes to negative infinity, hyperbolic cosine goes to infinity. So the graphs do look like this. We've talked about the derivatives. We have the graphs. There's one other fundamental property I want to talk about before I talk about the inverses of these functions. And that is why they're called hyperbolic trig functions. So why would the ordinary trig functions be called circular trig functions? You should recall that if you take the unit circle, so the circle of radius 1 centered at the origin in the xy plane, then ordinary sine and cosine are the x and y coordinates at points on this circle. So if you're at some angle t, yes, I know t is not a standard name for an angle, but if you're at some angle t and you let, then the x coordinate of this point is cosine of t, and the y coordinate is the sine of t. So the cosine of t, sine of t, if you let x be cosine of t and y be sine of t, that always specifies a point on the unit circle. Well, what about hyperbolic sine and cosine? Suppose I let x be hyperbolic cosine of t, and I let y be hyperbolic sine of t. Then do we get points that are on a circle? No, you should suspect what you get. You get points that lie on a hyperbola. So why is that? It's actually very easy to see. And it's the fundamental hyperbolic trig identity. Like sine squared plus cosine squared equals 1 is the fundamental circular trig identity. If you take hyperbolic sine, here's hyperbolic sine. So this is the hyperbolic sine of t. And you square it. Let's look at what you get. Well, let me go ahead and tell you what happens. If you square that and add 1, you will get, actually, let me just go ahead and write this whole thing. You'll get hyperbolic cosine, sorry. Here's hyperbolic sine squared, so since squared plus 1 equals the hyperbolic cosine squared. Why is that? Well, you just square it. You get, what do you get? You get, when you square this, you could get e to the t squared, which we could write as e to the 2t, but in fact, we'd have to undo that, so you might as well just write it as e to the t squared, minus 2 times this times this. But this times this is 1, e to the t times e to the minus t. So you get minus 2 times 1, so you just get minus 2. Plus this squared, which I'll still leave as e to the minus t squared. over 2 squared, which is 4. And then you add 1, which we write as 4 over 4. But when you do that, so now that we have a common denominator of 4, we just add 4, but that effectively that just changes this minus 2 to a plus 2. Right, so you end up with e to the t squared plus 2 plus e to the minus t squared over 4. This is exactly what we would have gotten had we squared this with a plus sign there. But that's hyperbolic cosine squared. This is e to the t plus e to the minus t over 2 quantity squared. But that's hyperbolic cosine squared. So this is the fundamental hyperbolic trig identity that, maybe I'll write it in a different order, 1 plus hyperbolic sine squared of t, or put any variable there, x, q, banana, Fred. 1 plus sinh squared equals cos squared. All right. I still haven't said why that means things lie on a hyperbola. I said, suppose you let y be hyperbolic sine and x be hyperbolic cosine, then this would say that 1 plus y squared equals x squared, or what's the same thing, I'm going to subtract y squared, but then so you get 1 equals x squared minus y squared, but I like to write it, the variables on the left. So let me take x squared minus y squared equals 1. So if you parameterize something, if you let x be hyperbolic cosine of t and y be hyperbolic sine of t, what you get is that all of those points lie on the curve defined by x squared minus y squared equals 1. You should recognize this from high school geometry. This describes a hyperbola, and that's why these are called hyperbolic trig functions. All right. I want inverses of the hyperbolic trig functions. So, what are they? Well, like we frequently have a little problem with functions where we have to restrict the domains to get something we can invert. That doesn't happen for hyperbolic sine. For hyperbolic sine of x, from the graph, we know the graph looks like this. It's 1 to 1. It passes a vertical line test. I'm sorry, that's why it's a function. It passes a horizontal line test, so that for any given y value, there's at most one corresponding x value. So it's 1 to 1. It's onto. It hits all the real numbers. So hyperbolic sine has an inverse. Okay? Inverse hyperbolic sine, and you can give it any real number, so anything between minus infinity and infinity, so anything in the entire real line, its domain, all real numbers, and its range. Its codomain and its range, all real numbers. All right, that's inverse hyperbolic sine. We'd like a formula for it in terms of functions we're more familiar with. Let me stop for a second, or let me hold off on that for a second and do hyperbolic cosine. Hyperbolic cosine is clearly not invertible. It doesn't pass a horizontal line test. If you take a horizontal line at y equals something greater than 1, it hits the graph in more than one place. We need to restrict the domain. We need to restrict the domain before we go on. So we artificially restrict the domain of hyperbolic cosine. So we take hyperbolic cosine, I'll write it with a capital C to indicate this restriction. It's a function that's defined from 0 to infinity, including infinity, and it goes onto its range is all real numbers greater than or equal to 1. And we define inverse hyperbolic cosine. When we write the inverse hyperbolic cosine, but with a lowercase c, exactly what we mean is the inverse of this function. So it's really, you take the inverse function of this one with the big C. What does that mean? The big C, it just means you've restricted the domains. And so the point of this is that the inverse function, it goes from here to here, so its domain is all real numbers from 1 to infinity, and its range, so its codomain and its range, the numbers from 0 to infinity. So what does this mean in practice? So what does it mean to say that x equals inverse hyperbolic sine of t, hyperbolic cosine of t? Well, in particular, it certainly means that the hyperbolic cosine of x, so this means the hyperbolic cosine of x equals t, but it also means that t better have been greater than or equal to 1, so, but that better be included as in part of your problem where you shouldn't be taking hyperbolic cosine of it. But it also means that what you get back, so this x has to be greater than or equal to 0. All right. So, all right. Those are inverse hyperbolic sine and cosine, but what are formulas for them in terms of functions we're more familiar with? Well, if we can actually do this. It's just the quadratic formula. It's fairly unattractive. Most people do not memorize this. They just leave answers in terms of inverse hyperbolic sine and cosine, and then if you're forced to, you either look up these inverse functions, or rederive them. It's not that they're ridiculously difficult to rederive, but they're not so easy. So inverse hyperbolic sine of x. Let's start with this one. This means, we didn't have to restrict any domains here. This means exactly that the hyperbolic sine of y equals x. So it undoes what inverse hyperbolic sine undoes what hyperbolic sine does. Great. But now we want to solve this for x. We want to solve this for y in terms of x, but in terms of functions we're more used to. So hyperbolic sine of y, that is, by definition, e to the y minus e to the minus y over 2 equals x. And we want to solve for y. Yeah, y is inverse hyperbolic sine of x, but we want to solve for y. As you might suspect, taking natural logarithms will come in. So inverse hyperbolic sine, if you want to write it in terms of functions you're more familiar with, natural log will be involved. So how do you do this? Well, first you multiply both sides by 2. So we want to solve this for y. So first you multiply by 2 and get 2x. Then you multiply through by e to the y. E to the y is positive. It's not 0 in particular, so that we're not messing. We don't have to worry that we've multiplied by 0 and destroyed information. Multiply through by e to the y. We get e to the y squared. Yes, that's e to the 2y, but actually it's better to leave it like this. Minus e to the minus y times e to the y, that's 1, equals 2x times e to the y. Put this part over here, and you get e to the y squared minus 2x times e to the y minus 1 equals 0. Now this probably looks awful to you, but we're about to use the quadratic formula. Think about it. Normally you have like an x squared minus something times x, and then plus some constant equals 0. So this is quadratic. It's just that what you normally have is x in the quadratic formula is the whole quantity e to the y, and where you normally have a constant, we have this thing involving, that's minus 2x. So what? It doesn't matter. Let me write the quadratic formula for a minute. Or let me take the time to write the quadratic formula, but I'll use a z to not confuse it with the x and y in our problem. So what you should know is that if you want to solve this, the quadratic formula tells you that z is negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay? Where we've got a z, that z is going to be e to the y. A will be 1. The z is e to the y. B will be the quantity negative x. And c will be negative 1. And so what we find, right, z is e to the y. So what we find from the quadratic formula is e to the y is negative b, so negative 2x, plus or minus the square root of b squared, that's 2x, or negative 2x, quantity squared, minus 4 times a times c, a is 1, minus 4 times 1 times minus 1, so plus 4, all over 2a, so over 2. So we get this. So we just found that e to the y equals 2x plus or minus the square root of 4x squared plus 4 over 2. You can factor out a 4. The square root of 4 is 2, and then all the 2's cancel. So this is x plus or minus the square root of x squared plus 1. Now we don't want a plus or minus. How do you decide? Well, e to the y is positive. We have to end up with something positive. X squared plus 1 is greater than x squared. So that quantity is greater than the square root of x squared, which is the absolute value of x. So this quantity is greater than the absolute value of x. If we subtracted it, whether x was positive or negative, we would end up with a negative number. But e to the y can't be negative. So here we have to have plus. And so now we take natural logs, and we get y is the natural log of x plus the square root of x squared plus 1. So if you want to write inverse hyperbolic sine in terms of functions you're more familiar with, this is what you get. It's not very attractive, but it's what you get. I leave it as an exercise for you to verify that. So the inverse hyperbolic cosine by a similar argument, but you have to worry about the restricted domain of the original function, so codomain of inverse hyperbolic cosine. It looks almost exactly the same, except you have a minus sign right here on the 1, which, right, inverse hyperbolic cosine, its domain is all numbers greater than or equal to 1. Well, good. I mean, because if we put in something, if you put in something like between 0 and 1 in here, like if you put in a half, the square root would be undefined. But, right. This is what you get for inverse hyperbolic cosine. All right. We'd like derivatives of the inverse trig functions because they come out to be very nice. Even though the formulas for the trig function, the inverse trig functions themselves, are not so nice, their derivatives are nicer, which is a little weird, but still, that's the way it is. So what I would like to do is find the derivative of inverse sine of x. We could use the formula for inverse sine, but we have a kind of a general, it's a little nicer, and it's a little more interesting to use, we know how to find derivatives of inverse functions in general. There's a formula for it, but it's not as though you need to have it memorized exactly because you remember the chain rule. So inverse hyperbolic sine of x, if you then do hyperbolic sine to that, well, they're inverse functions. You just get x. And this is an identity. It's true for all x. So we can differentiate both sides with respect to x, and we still get an equality. But over here, you use the chain rule. You differentiate the outside function, the derivative of hyperbolic sine, though, is hyperbolic cosine. You leave the inside stuff exactly how it was, but then by the chain rule, you have to multiply times the derivative of the inside stuff, which is why this is going to give us a formula for the derivative of inverse hyperbolic sine. You get that equals the derivative of that side, but that's 1. So what you get is that the derivative of inverse hyperbolic sine of x is 1 over hyperbolic cosine, so cosh, of the inverse hyperbolic sine of x. This is not terribly attractive. I said you get a nice formula. Well, you may think this is nice, but can we write the inverse hyperbolic cosine of the inverse hyperbolic sine in a nicer way? And the answer is yes, we can. It helps to call this something temporarily. So why don't we call this inverse hyperbolic sine of x? Let's call that y temporarily. So if you let that be y, so if we let y equal inverse hyperbolic sine of x, exactly what that means is that x is the hyperbolic sine of y. And this would just become 1 over the hyperbolic cosine of y if we called this y. So the question is, if we know x equals hyperbolic sine of y, can we write the hyperbolic cosine of y in a nice way? And the answer is yes. We use the fundamental hyperbolic trigonometric identity. We know that 1 plus hyperbolic sine squared of y equals the hyperbolic cosine squared of y. So this means that but this is 1 plus x squared. 1 plus x squared equals hyperbolic cosine squared of y. And you take square roots of both sides, so you get the square root of 1 plus x squared equals, and now you have to be slightly careful, the square root of something squared is not always the original thing, it's the absolute value of it. So the square root of hyperbolic cosine squared is the absolute value of hyperbolic cosine of y. But hyperbolic cosine is always positive, so it is its own absolute value. So that, yes, we do get that hyperbolic cosine of y is the square root of 1 plus x squared. So that's what we get. 1 over the square root of 1 plus x squared. Just so I can write that in a similar formula for the derivative of inverse hyperbolic cosine, I'm going to put the x in the denominator first. So the formulas that you get, the derivative of inverse hyperbolic sine, 1 over, I wrote it as the square root of 1 plus x squared. Now I'm going to write the square root of x squared plus 1. So that for hyperbolic cosine, I can write something that looks very analogous. Again, I leave this to you as an exercise, doing essentially the same thing, but having to be a little careful about domains and codomains. You get the derivative of inverse hyperbolic cosine of x is 1 over the square root of x squared minus 1. We haven't done any integration yet, and that should kind of bother you. Well, this is the reason we want the inverse trig functions, inverse hyperbolic trig functions. Because if you read these as integration formulas, or as anti-differentiation formulas, this one says that this is inverse hyperbolic sine plus c, and this one tells us that this is inverse hyperbolic cosine of x plus c. Now, should you memorize these? Well, it depends on your instructor. I would say, for my own students, I would say no. What I expect my students to know fundamentally is that I expect them to know what hyperbolic sine and cosine are, the definitions in terms of E. And then I expect them to know the fundamental hyperbolic trig identity. And I expect them to know or rederive from the definitions, because it's so quick, that the derivative of hyperbolic sine is hyperbolic cosine, and the derivative of hyperbolic cosine is hyperbolic sine. If you know these things and you come across one of these integrals, or in a minute I'm going to put an a squared there and do those, you can make a substitution that gives you these formulas quickly without having to know the formulas for the derivatives of the inverse hyperbolic trig functions. So let me show you how that goes, since that is what the point of this section is. How do you use these for integration, for finding antiderivatives? So, suppose, example, fine. So suppose a is a constant greater than 0. Let's find a nice formula for this antiderivative. We could use normal trig functions here. You could make the substitution that makes x equal to a tan theta. So that really means you're defining theta to be the inverse tangent of x over a. But if you make a substitution that turns x into a tan theta, then you get a squared tan squared plus a squared. Factor out the a squared. You get the square root of a squared, that's a, because I'm assuming a is a constant greater than 0, times the square root of tan squared plus 1. But tan squared plus 1 is secant squared, and you do what you do, and that will work out. But it's much harder than what happens when you make a substitution using hyperbolic trig functions. So how should you think about this? If you remember the hyperbolic fundamental trig identity, so now I'm going to write it in terms of t, because we have an x in the problem already. The fundamental hyperbolic, maybe I'll use u, since that's our favorite name for a substitution variable. Our fundamental hyperbolic trig identity is this one. How does that help you? What you try to do when you see something squared plus something squared under a square root, you want to make the thing under the square root essentially equal to this, but you also have to throw in a constant to factor out the a squared part. So that's what we do. You should think to yourself, if I could make x equal, so what we want, you want x equals a times the hyperbolic sine of u. What? Why do you want that? Because if x is a times the hyperbolic sine of u, then x squared is a squared hyperbolic sine squared. You have an a squared both places, you can factor that out, and then you're left with hyperbolic sine squared plus 1. And so you get hyperbolic cosine squared, you take the square root, you get hyperbolic cosine. What's nice about this is if x is this, then dx is the derivative of this times du. And the derivative of hyperbolic sine looks like, it looks like stuff involved in the problems, hyperbolic sine and cosine. The derivative is hyperbolic cosine. So that's why that substitution works. It's the same reason why a tan theta works. Because not only do you get the square root of secant squared down here, but the derivative of a times tan theta is something that involves more trig functions. So you get something very similar to the other things in the problem, and you can hope to finish. So this is what we want, but you don't get to define x to be this. X and a are already in the problem. So really what this means is we let, but a lot of people don't bother writing this part, but it is important in other problems. So what we're really letting happen is divide by a and then take inverse sine. We are letting, right, so this is x over a to equal hyperbolic sine of u, but u is the undefined thing. We're letting u be the inverse hyperbolic sine of x over a. But that means exactly this, that x is a sine of u. And so what do you get? Well then, you get that this becomes the square root of x squared is a squared hyperbolic sine of u squared, and then there's plus a squared. And dx is the derivative of this, so that is a times the derivative of hyperbolic sine is hyperbolic cosine of u times du. So once you've made this substitution, this is what you get. You might look at this and go, yuck, but you shouldn't. This is very good. We can factor out an a squared, so you get that. But now the square root of a squared is just a because a is positive. If a were negative, well, the square root of a squared is the absolute value of a. So if a were actually a negative number, square root of a squared would be negative a. But we don't have that problem. You get, when you factor this part out, square root of a squared, you get a. It cancels with this a, so these go away. Sine squared u plus 1 is hyperbolic cosine squared. The square root of that is the absolute value of hyperbolic cosine. Hyperbolic cosine is always positive. That's hyperbolic cosine. So what you get is the integral of 1 over hyperbolic cosine of u times hyperbolic cosine of u du. These cancel. You get the integral of 1 with respect to u. Wait, I'll do it in my head. That's u plus a constant. But what's u? It's the inverse hyperbolic sine of x over a. And so that's our final answer, that you don't have to memorize that this is what you get. It's very quick by knowing fundamental properties of hyperbolic sine and cosine, namely the fundamental hyperbolic trig identity, and then that the derivative of hyperbolic sine of u is hyperbolic cosine of u. You immediately, well, very quickly get that this antiderivative is the inverse hyperbolic sine of x over a plus c. Of course, if you want to write this in terms of functions that don't explicitly refer to inverse hyperbolic trig functions, then you have to use the equality that we proved for what the inverse hyperbolic sine is. So the inverse hyperbolic sine of a quantity t is the natural log of t plus the square root of t squared plus 1. But if you're allowed to leave inverse hyperbolic trig functions in your answer, this is it, and you stop. I want to do the analogous example with inverse hyperbolic cosine, just so you can see where the slight problems come in with hyperbolic cosine, or where you should be a little more careful. Most people aren't, and if you weren't careful, you'd still get the right answer, which in a way is kind of annoying. But let's do another example. So let's look at this one, this integral. All right. So knowing the fundamental trig identity, what you should accept, which a minute ago I wrote as 1 plus hyperbolic sine squared equals hyperbolic cosine squared. When you see something squared minus a constant squared, you should think, oh, what I'm going to use is this, but with the 1 subtracted from both sides. So this. And what you'd like to do is you want x to equal a times the hyperbolic cosine of u. Why? Because if x is a times hyperbolic cosine of u, x squared is a squared over times hyperbolic cosine squared. You can factor out the a squared from there, and you're left with hyperbolic cosine squared minus 1. But there's hyperbolic cosine squared minus 1. It's sine squared. You'd have its square root. You get hyperbolic sine. And then dx, again, is easy to find in terms of hyperbolic trig stuff. It's a times the derivative of this, which is hyperbolic sine of u times du. So this will be nice. But you don't get to pick what x is. You actually pick what u is. So what this means, so let u equal the inverse hyperbolic cosine of x over a. Now, I didn't say it again here, but I meant to, that I'm still assuming a is greater than 0. Notice that x has to be, either greater than a or less than negative a. We are, in fact, going to assume here that we're looking at this function when x is greater than a, so that we're not dividing by 0, but it's also important that we also want x over a to be greater than 1. So since a is positive, we can divide this inequality by a, and it doesn't change. This is the same as saying x over a is greater than 1. This is important now because try to remember the domain of inverse hyperbolic cosine. Well, it's kind of the range of hyperbolic cosine. So that's all numbers greater than or equal to 1. So we can only take inverse hyperbolic cosine of something greater than or equal to 1. Why aren't we allowing it to equal 1? Well, we don't want x to be a in this denominator. All right, so we need this. We're only doing this for x is greater than a. So this is part of the subtleties that if you didn't notice would work out, but we're assuming that. But this also means something else. Remember that the range of inverse hyperbolic cosine is our restricted domain on hyperbolic cosine. So our restricted domain was, we could only put in numbers greater than or equal to 0. So when you let u be this, in particular, we need x over a to be greater than or equal to 1. So we need this. But this also means, this implies that u is greater than or equal to 0. Because it's something we get out of inverse hyperbolic cosine. You need to know those things, but as I said, if you ignored them, things would work out, but in other problems it might not. So it's good to pay attention to them sometimes. All right, but now that we've said all that, you do essentially what we did in the last problem. This is now 1 over the square root of x squared minus a squared. That's the square root of a squared hyperbolic cosine squared minus a squared dx is the derivative of this times du. That is a times the derivative of hyperbolic cosine, hyperbolic sine, times du. We get this. Again, you have the square root of a squared, and a is positive. So the square root of a squared is just a. We factor out the a squared here and here. Then the square root of a squared is just a, which cancels with this a. So those get wiped out. The square root of, so let's do this. So this is the integral of 1 over the square root of cosine squared of u minus 1. That's hyperbolic sine squared. And again, if you're not being careful, what you would say is, oh, the square root of hyperbolic sine squared is hyperbolic sine of u, and that cancels with this, and again we get the integral of 1 du. It's true, but that ignored something important. The square root of hyperbolic sine squared is the absolute value of hyperbolic sine of u. But hyperbolic sine of u could be negative in general, right? It's not like hyperbolic cosine. Before we had the square root of hyperbolic cosine squared. That's the absolute value of hyperbolic cosine of u. But hyperbolic cosine was always positive, so we didn't need absolute value signs. Here, we only know that hyperbolic sine of u is positive when u is positive. Oh, but our u is positive. It's certainly greater than or equal to 0 because it's the inverse cosine of something, but we're not allowing x over a to be 1, which means we're also not allowing u to be 0. And we're not going to get back u as 0 because that's when hyperbolic cosine is 1. So in fact, we're assuming u is greater than 0 by letting u be this. And so that means the square root of sine squared of u, which is the absolute value, did I say sine, hyperbolic sine squared of u, that this absolute value of hyperbolic sine of u is in fact just the sine of u, because since u is positive, hyperbolic sine of u is positive. So this square root of hyperbolic sine squared just becomes hyperbolic sine of u. It does cancel with this hyperbolic sine of u, and you do get the integral of 1 du. That's u plus a constant. And then you put back in that u is inverse hyperbolic cosine of x over a. So yes, what you get fairly quickly is that this integral is the inverse hyperbolic cosine of x over a plus a constant. All right. Well, those are all the examples I wanted to do. Hyperbolic sine and cosine just give you two more tools, one or two depending on how you count, one or two more tools for helping you find anti-derivatives. It's if you're allowed to leave your answer in terms of inverse hyperbolic sines and cosines, these problems are fairly easy. If you, in the end, aren't allowed to have those functions, then you either have to memorize the formulas for inverse hyperbolic sine and cosine in terms of natural log, or you need to rederive them quickly at this point. But it's good to know that that approach works. If you're just trying to decide, can I do this integral? Can I find this antiderivative? Yeah, once you've got this, you know that you can do it. And then it's just a question of how you're allowed to leave your answer, and do you need this other algebraic formula? But at least there's no integration problem left. All right, that's all I want to say about this section.